This video is going to continue our discussion about inverse functions and how to find the derivative of inverse functions. So just to start off, I'd like to remind you what an inverse function is and sort of how it works. We're swapping x and y's, we're swapping outputs for inputs and generating inverse functions in that manner. So think for a minute about e to the x. The inverse of e to the x would be the natural log. And to undo something like x squared, I would want to take the square root. So we want to kind of think about inverses as undoing mathematical operations. If I have the sine of x, the inverse of that would simply be inverse sine, or as we saw in the last video, we'd call that arc sine of x. And the composition of inverse functions essentially cancel out. So e to the power of natural log of x leaves me with the argument of x. So generically speaking, the function f has for its inverse f inverse of x, and we'll denote that inverse with a little tiny superscript -1 on the function. So what I have for you here in this video is an exploration on what is going to happen with derivatives of inverse functions. So let's look at this function x to the third. Remember that to find the inverse, we want to swap x and y, so I'll call that x equals y to the third. And if I solve for y, I'll have y equals the cube root of x. So there's my inverse function, and we're going to use g of x as notation for the inverse in this case. And number 2 says to draw a quick sketch of f and g. So here's the function x to the third on the f of x graph. And then over here, I have the function of cube root of x on the g of x graph. And remember that derivatives are always slopes, slope of the tangent line at various points. So let's find the derivative. F prime of x, well, that would be 3x squared. And then this is x to the power of 1/3. So the derivative of the inverse would be 1/3 x to the negative 2/3. And let's just kind of see what is going on here with the slope of the tangent line drawn to the function and then draw to the inverse function at these various points. So at 1, 1, in other words, what is f prime of 1? And then what is f prime of 2? And what is f prime of 3? So do a little bit of calculation here. We should end up with 3 and then 12 and finally 27. And then let's shift gears and think about the inverse for a moment. So find the slope of the tangent line drawn to g at these points. So what is g prime of 1, g prime of 8, and then g prime of 27? And remember that inverses swap the x and the y's, so those are backwards. Instead of 2, 8, we have 8, 2. Well, plug in 1 and let's see what we end up with here. It should be 1/3. Plug in 8 into our inverse function and we should end up with 1/12. 1/12. Plug in 27 into the inverse function and we should end up with 1/27. And so what I hope you start to realize is that the derivatives of these inverse points end up being the reciprocal of the derivative of the function at that point. So there's this reciprocal relationship that's taking place here between inverse and original function. Now, what does all this mean for us with calculus? Well, here's what it means. Consider this example over here of a new function, 1/4 x cubed plus x minus 1. Our task right now is to find the derivative of not f, but the inverse of f. So find the derivative of the inverse of f. And to do that, I'm going to take you through a little bit of a scaffolding series of questions here. So let's first find f of 2. Plug in 2, we should get an output of 3. And if 2, 3 is my ordered pair, then that means 3, 2 would be the ordered pair on the inverse. Here's my inverse function. And to find the value of f inverse of 3, essentially what they're asking you for is what is the input that gives you 3 as the output. Inverses just kind of switch switch input and output. So number 4, and here's where we're going with this. It says, considering the observations from the exploration, what is the value of the derivative of the inverse function when x equals 3? And what I tell students to do, and I think this is helpful, is we're going to make what I call a point derivative table. So if you could sketch a little table like this, it's simply a 2x2 matrix almost. We're going to start in the lower left-hand side of this table, the intersection of F inverse and the column that says point. So the point should be given to you. They're telling us at 3. So we're going to write 3, comma, and remember that if it's an inverse point, then 3, 2 will be that output. But we don't want to live here on inverse land. Let's go back to the function and perform some calculus on the function. So if 3, 2 is the inverse point, let's move up the column and write the original function's point, and that would simply be 2, 3, because inverses swap the x and the y. So now let's move over to the derivative column. What is f prime of 2? F prime of 2. Not inverse of f, but regular f. Well, let's come back here and do a power rule. F prime of x on this thing would be 3/4 x squared plus 1. And I want to plug in 2, so f prime of 2 is going to be 3/4 of 2 squared plus 1. So that looks like 3 plus 1 for a value of 4. F prime of 2 is equal to 4. And then what we do is travel back down the table into inverse land once again. We want to be on this inverse row. And my final answer is simply going to be the reciprocal. The reciprocal of whatever number I wrote right here. So the derivative of my inverse function will be 1/4. And that's my final answer. So what essentially we've done is gone from the inverse point back to the function point, the regular function point. We did a little bit of calculus here to find out what the derivative was. We found our value of the derivative on the function, and then we just recognized the fact that we have a reciprocal relationship. So whatever that value is here, the reciprocal of it would be my derivative of the inverse at that point. Now, to illustrate this a little bit further, I'd like you to take a look at a series of a few more examples, and I wrote them down here below. 2 more examples. So here I have a table. I have 3 columns, a table of x values in blue, some inputs into my function. Then I have the function outputs here in purple. And then notice this, I have a few derivative outputs as well of f. So f prime values and f values, and then the inverse value, or the x input values. And what I'm interested in knowing here would be the examples listed in orange. Let g of x represent the inverse of f. Example 1, find the derivative of the inverse when x equals 16. And then example 2, same question, but just a different input. Find the derivative of the inverse when x equals 4. I'm defining g of x as the inverse of f. So again, I'm going to go to this little point derivative table format here. Let's see if we can figure out the solutions. So we're going to be given a point. In this case, for example 1, my point is 16. So my inverse point will be 16, comma, something. Let's find out what the match is to 16. And remember that we're on an inverse right now. We're on an inverse, which means 16 is an output. What was the input that gave me 16? It looks like the match there would be 2. So 16, comma 2 is the inverse point. Now, we're going to start there and move back to the function. If the point on the inverse is 16, 2, then the point on the function must be 2, 16. I'm trying to find a derivative, so let's travel to the right and move over to the derivative column. What's f prime of 2? Go to the table, and let's see here. F prime of 2 appears to be the number 25. So f prime of 2 is equal to 25. And that is enough information for me to get to my solution. The derivative of the inverse will come back down here to the inverse row, and we'll write our reciprocal of 25, so 1/25th. And that's my final answer. The derivative of the inverse, or g prime of 16, is equal to 1/25. We'll do that one more time. Down here, what about g prime of 4? So the given point is 4. Now what's the match to the 4 right there? 4 is an output. I want to find the number that was the corresponding input. Now be careful we don't go down here and put down 256. 256 is an output. We're searching for a corresponding input. So 4, 1 would be the inverse point, which means 1, 4 would be the sort of original function point. So travel up there. Now travel across here. We want f prime of 1. F prime of 1. According to the data, f prime of 1 is equal to 16. So the derivative of the inverse, final answer, is 1/16. I like the point derivative tables. It just helps to organize the data. It helps organize the points. And you start with the point that you're given, you move back to the function, and then back around and end with the reciprocal relationship. Inverses are tricky, they can be challenging, so take your time and work through these problems, and feel free to use this table setup to help you find success at writing derivatives of inverse functions. Thanks for watching.